So the last two lectures, we proved this theorem. I didn't give it an author because it's a quite classical theorem. So this is for hypoelliptic differential operators with constant coefficients on Rn. And then in the second lecture, I described this theorem and some idea on this proof, which gives you hypoellipticity for left invariant homogeneous differential operators on a graded nilpotent Lie group. Now there is an extension to this theorem, which there's an addition to it, which I didn't really have time to describe, which says the following. So furthermore, it's true for both of them. If D satisfies the above, and D prime is of lower order than D, then the sum is again hypoelliptic. You actually don't need that. But and here also you don't need you don't need it to be left invariant. So furthermore, but that's harder to prove. It's also true.
What do you say if you D plus D prime?
Is hypoelliptic.
The sum now is.
Yeah. It's an elliptic differential. Yeah, it's strictly lower, of course, because otherwise I could just take minus D and if it's not clear, my favorite example is 0. Furthermore, if D satisfies the above, then D plus D prime is hypoelliptic if D prime has lower order. And just to clarify a little bit, lower order here means with respect to the grading. So here this is the usual order, but here when we said homogeneous with respect to the grading of the group. So lower order means that it's sum of homogeneous terms. Each one of them has strictly lower order. Okay. And I gave an exercise which gives an example of this theorem, and let me give you a proposition giving you a general result. So proposition. So let G be a graded nilpotent Lie algebra and so by definition I can write it as a direct sum, and let x1 some elements of G1 such that G is generated by XR, by this element. Obviously, this doesn't necessarily exist. Maybe G1 is 0. Suppose generated, not as a vector space, as a Lie algebra. So it's linearly generated by these elements and the Lie brackets. So, i.e., linearly generated by X and X Lie brackets. I think you then x1 square plus xk square is hypoelliptic. And here I see this as sum of left invariant. The Lie algebra is the Lie algebra of left invariant vector fields on the Lie group, so I can see elements of the Lie algebra as left invariant vector fields. So this is a sum. So this is a left invariant differential operator, which is homogeneous of order 2. And it will satisfy this hypothesis, and so we get immediately that it is hypoelliptic. Okay. A small remark. I suppose that these elements here are in G1. I could also suppose that they are in general in G whatever, or even they don't need to be in the same graded component. It's just that this one will have to be homogeneous. So I will change the powers. Here I choose powers of 2 so that all of them have the same order. If they have different orders, then I choose an even power using the least common multiple so that they have so that they are homogeneous. Okay, and the proof of this fact uses this theorem. So the proof is very simple. So if pi is an irreducible unitary representation, and V is some vector, some smooth vector such that, so I call this D. So pi of D, V is equal to 0. Okay, so I need to show that it's injective for non-trivial representation. And so I will take an irreducible unitary representation and a vector which satisfies this, and I will show that either V is 0 or the irreducible unitary representation is trivial. This is very simple because this thing is a sum, so it's x1 squared plus pi of xk squared. So this thing, so this. And each pi of xi is anti-self-adjoint. This is because the representation is unitary, and this is the differential of the representation. So you get anti-self-adjoint. And so the square is a negative operator. So this is a sum of negative operators applied to V. You take the Lie bracket with V, and so you deduce that. So take Lie bracket this. And then you deduce that pi of xi v is equal to 0 for all I. You just put the xi. So you have sum of negative elements, which gives you 0. So each one has to be 0. And now here we use that the Lie algebra is generated by the xi, because if pi of xi is 0, then pi of the Lie bracket is also 0, because this is the commutator of these two maps. If each one of them vanishes on an element, then the commutator vanishes. And so this is also equal to 0, etc. for higher generators. And so pi of x v is equal to 0 for all x in G. But then this means that it's an invariant vector. So either the vector vanishes or the representation is the trivial representation. Now, there is an analogous result to this one, which yes?
Excuse me, you said that this also holds for, well, you do not have to have the sum of squares, but homogeneous is also okay, but I do not see from the proof how to do that.
If it's sum of even powers.
Okay.
Yes. I mean, the point was that each one will be, I mean, you need that each term is negative so that, or positive. So
You have to represent
yet. I mean, you have to make sure that it's sum of either all positive operators or all negative operators. Okay? Now, there is an analogous result. So till now, I have only been discussing differential operators which are invariant on groups. And the question is, well, how do we deal with differential operators which have variable coefficients, say something like sine x or something like this? So there is an analogous result to this one by Hormander, which actually precedes this one. So let M be a smooth manifold. And x1 vector fields, and I always say vector fields mean real vector fields, so vector fields. We say that these vector fields satisfy Hormander's condition of depth n. N here is plays an analogous role to the n in the Lie group. Okay, so some natural number. If for all x in M, the tangent space is linearly spanned by the vector fields at the point and their commutators and their iterated commutators, etc. up to commutators of length n, up to of length n. So an example to make it easier. So on Rn on R2, you could just and you fix and let k some natural number. Then you take x1 to be dx and x2 to be x power k dy. So they linearly span the tangent space except if x is equal to 0. But if x is equal to 0, this one vanishes. But if you take enough commutators, you are good. Because the commutator of x1 and x2, but this is just k x power k minus 1 dy. And then you iterate. And after enough iteration, k iterations, you will just end up with k factorial ky, dy. Okay? So this is an example of two vector fields which satisfy Hormander's condition. Now, a theorem by Hormander, which is 67. This is probably the only part I prepared. Yeah. So Hormander, so he proves the following. So again, M is a smooth manifold and X are vector fields satisfying. Then the differential operator D is hypoelliptic. So we see that it's a very analogous result to the one above, but it works for any smooth manifold. You don't have to, this one works for groups, but this one works for any smooth manifold. Okay? And notice that this result applies to some more interesting example. So, for example, I could twist a little bit this example. So on R2, I could take dx. So this is my first vector field, and I could take the second vector field, which is sine of x power k dy. They will again satisfy Hormander's condition. But the point is that if I take k plus 1 commutators here, between x1 and x2, they will vanish. And so this behaves almost the same as above, because it behaves as if I was in an nilpotent Lie group. But here it doesn't. The commutators will never stop from, will never give you 0. Just that after k times, you will reach a function whose derivative doesn't vanish. Okay? Using the fact that half of my students in L2 know, which is that sine x is equivalent to x. I think half of them know it, I think. Anyway, so actually, this theorem by Hormander, so as you see this result by Helfer and Origa, this is an old, this result by Hormander is older, came before the theorem by Helfer and Origa. And the proof by Hormander, they don't generalize Hormander's proof. In fact, what I have is that, what we have is that Rothschild, this I also wrote, Rothschild and Stein in 76 showed Hormander's theorem using the above corollary. So Rothschild and Stein, they show that this theorem by Hormander, you can prove it using this corollary. Okay? Even though the differential operators are different, they live in different manifolds, you can kind of deduce it from the above. I really don't have time to give you the proof of this, and it's quite technical, but you can do it. Now this promoted Helfer and Origa to make the following conjecture, which is, suppose you have a differential operator, which some formula, using some vector fields, using these vector fields, x1 and xk. And suppose that this formula, not necessarily sum of squares, some other polynomial, suppose that it satisfies this condition, this injectivity condition, so it is hypoelliptic. So if you have such a formula, then they conjecture that the exact same formula on any smooth manifold will again give you a hypoelliptic differential operator. So this would work, this implication corollary to theorem would work for any polynomial, not just the sum of squares. Now, there's what I just said, they actually knew how to prove it. What they conjectured was actually stronger than this, which is that actually for any smooth, so here in this condition, you have all your representations. So they conjecture that if you work with the free nilpotent Lie group, which I will describe in a moment, then for any manifold, there is some set of representations, which depends only on the manifold, such that you don't have to check this condition for all representations, only the representations in this set. Okay? And if it happens that you have this injectivity, then the differential operator on that specific manifold will be hypoelliptic. Questions? Yes? No, it can be anything. Actually, Hormander's theorem is a tiny bit more general in the sense that he says that you could actually, here I suppose that it is bounded. He doesn't suppose that it's bounded, but it doesn't really matter because hypoellipticity is a local condition, and so you might as well suppose that it's bounded. And he's the first step, he says, okay, I can suppose that it's bounded, this doesn't make any difference. Yes. So the first step I will describe. So in this talk, the whole talk, the goal of it is to present a joint work with Androladakis who's the chairman, and I should respect the time, and Yunkin, who's not the chairman, so I don't have to respect the time to him, which answers positively this conjecture of Helfer and Norgay. So I have the free nilpotent group. So there is this object called the free nilpotent Lie group, which is essentially the biggest Lie group, Lie algebra, Lie group, which is of depth n and k-generated. This means that G, so it's a direct sum. And it's free in the sense that you have, so the only conditions, are the fact that it's a Lie algebra and the Jacobi identity. Who knows what it is? And the third condition is that Lie brackets of depth bigger than n vanish. Yes, it is generated, so it satisfies the same condition as the one in the corollary. So the way you construct this thing, you take the free Lie algebra. This is a classical construction. You can find it in Serre's book. And all you have to do is just, if you have any commutator which uses more than n commutators, you just divide by this vector space generated by all of these. This vector space is an ideal, and so the quotient is a Lie algebra, and it's graded. The grading comes from the number of commutators that you use. This is a well-known construction in G1 is of dimension k. And the dimension of G2 would be all commutators, and you have the anti-symmetry, so it's k. Who knows what this is? Probably this. And I can tell you that there is a formula for the dimension of the whole Lie algebra. This is known. And okay. Exercise, find it. Yes, this is correct. I saw this. Now, as I said, their conjecture involves a specific set of representations. And so I want to, they didn't say there exists a set of representations. They actually gave a formula for this set. And to describe this set, I have to tell you that, so we know how to classify representations of nilpotent Lie groups. This goes before Helfer and Norgay, and it's Kirillov's, I know how to write his name. So it's orbit method, which gives bijection between G star, the dual of the Lie algebra, and the quotient of G by G star. So the group G acts on the dual of the Lie algebra by the coadjoint action. This is quotient by the coadjoint action. And more or less, we saw hints of this theorem in yesterday's talk on the theta correspondence with the Heisenberg group. But it's true for any nilpotent Lie group that you have a bijection between irreducible unitary representations and coadjoint orbits. And it's not an abstract bijection. Kirillov tells you how, starting from a coadjoint orbit, you can construct the corresponding representation. And it behaves in a very nice way. It's continuous. It's a homeomorphism. If here you put the Feld topology and here you put the quotient topology from the Euclidean topology in G star. So it's a homeomorphism. It sends the trivial representation to 0. The coadjoint action is linear, so 0 is an orbit. Okay. So it's a very nice bijection, and they describe it using this bijection. So I want to go up. I want this to go up. So now I take G to be the free nilpotent Lie algebra. Free nilpotent Lie algebra. Notice that the number of generators I take is the same as the number of vector fields I have. Okay. Then we have a canonical map which goes from G to vector fields of your manifolds. I have k generators in my Lie algebra. Let's call them x1 till xk, just like the vector fields. So it sends xi to xi. So this is the generators. Okay. I have the G1, as we said, has dimension k. So you send xi, call the generators xi to xi. Well, okay, but this is not everything. What about commutators? Well, you just send them to commutators. And so on, it sends xi and xj to xi and xj, and so on. But be careful, this is not a Lie algebra homeomorphism. So not a Lie algebra homeomorphism. The reason is because of this example with sin x. I can have commutators so in the group, once I reach n commutators, any commutators after this will vanish. But here the commutators don't necessarily vanish. So it's a Lie algebra homomorphism up to some certain commutators. Once I reach these commutators, it stops. Yes. Yeah, he's also Greek, so time and Greek. I'm good. So it's not a Lie algebra homomorphism, but that's not really.
Unless you have the bracket generating condition.
No, it's a problem with the fact that sometimes my vector fields in Hormander's condition, sometimes the vector fields don't necessarily, after n plus one commutators, they might not vanish. It's the same as taking sin x. Actually, usually it's not a Lie algebra homomorphism, except if your manifold was certain type of a group or a quotient of a group. Yes?
I'm sorry, I don't understand why the generator is on the side of vector field on the right.
What? I don't have. Yeah, so I might not have stressed this, but I'm fixing some choice of vector. My vector fields which satisfy Hellman's condition, I'm fixing them for the rest of the talk. This doesn't change. Now, I have a map from G to Lie to vector fields. And so for if X is in M, I can define this map which takes an element and gives me this evaluated at X. Okay? So I take my vector field and evaluate it at X. And Hormander's condition, notice that Hormander's condition a fancy way of writing it would say that this is the same as saying that for all X in M, this map is surjective. This is the exact same thing. It just says that the vector space Txm is linearly spanned by the xi evaluated on X and their commutators. And now, so the idea of Hellfent-Origa is to take cotangent vectors. Remember that if I want to construct representations, I have to construct elements in G star. And so the idea is I take cotangent vectors here and pull them back using this map. And so the set, I should go up. No, this goes down. And this goes, this is number 3. No, 2. This is so fun. I can't be more sarcastic. So definition. So let X be in M. So I lied a little bit. The set of representations not only depend on the manifold, it also depends on a point in the manifold. This is natural because differential operators have coefficients which are C-infinity functions in the manifold. And so they don't exactly come from formulas from the group. It also depends on the point in the manifold. And so it's defined as follows. So I use Tx. So it's the set. So it will be a subset of the dual of the Lie algebra. And so you can find xn, a sequence which goes to x in M, so sequence in M. And you can find a Tn which goes to 0, so a sequence of reals positive goes to 0, such that xi, yeah. Sorry, it's easier to write it this way. So I take the kernel of this map. It's not easy, it's more conceptual to write it this way. I take the kernel of this map, and it's a subspace of G, and it has codimension. Then I apply alpha 1 over Tn of this set. The formula is this one. I will write it and then try to explain where it comes from. So it's union of V orthogonal it is this set. Where does it come from? I have this map. It is surjective. Okay, so I look at its kernel. So if I quotient by the kernel, then it will give me a linear isomorphism. And so if I take the dual, then it will give me an isomorphism of this, an isomorphism with kernel of natural X orthogonal. Okay? So the cotangent space is a subset of the kernel. You can see it as a kernel. And so in some sense, what you want to do is you take all of the cotangent spaces, but not at the point, but at all of the points which are around this. Okay? And you have to use the dilation. So this is the dilations in the group. Yes? Yeah, so this is the dilation on the Lie algebra. I mean, I had to use grading. There is a grading on the. Here there was homogeneous with respect to a grading. So alpha. So it's a map. So it's alpha. So if lambda. So it's a map which sends x. If it's in G1, it multiplies by lambda. If it's in G2, it multiplies by lambda square x, and so on. It's a Lie algebra homeomorphism. Yes, I mean, two days ago. The formula itself is not. There are better ways to define this. Their way is not really the best way to do it, but it's. But what I want to say is that it's very computational in the sense that if you have a specific manifold and you have a specific vector field and you want to compute this set, you can sit down and in 20 minutes you will figure out what the set is. Okay?
What do you mean precisely by that space alpha?
Yeah, so this is convergence in the Grassmannian topology.
No, what is the arrow?
What arrow?
Between alpha and V.
Yeah, converges in Grassmannian topology. Okay. Now a non-trivial result. But this is a subspace of the Lie algebra. This is a subspace of the Lie algebra. So the limit is a subspace of the Lie algebra. The orthogonal is dual in the Lie algebra G star. So the linear maps which vanish on V. Now, what's not clear at all from the formula is that this set is closed. So it's a subset of G star. It's closed with respect to the Euclidean topology, and it's closed under the coadjoint action. So it's some set of orbits. So we can think of Okay. Now I can state the theorem 45 minutes into the talk. I want to erase this. So let P be a polynomial. So it's polynomial, non-commutative polynomial. In k variables with coefficients in C infinity of m. So when I said take some formula, sum of its squares, that's a non-commutative polynomial. Non-commutative because vector fields don't commute. So if I have such a polynomial, then I can take the polynomial, then I remove each variable and put the vector field. So this is a differential operator on M, which I want eventually to prove that it is hypoelliptic. And as you see, I'm allowing also coefficients to be C infinity functions, which I did not have in Hormander's theorem. I just had sum of the squares, but I didn't. I can also multiply with C infinity functions. Okay? So now I need to define this to write this condition. So I have to define, so if x is a point in M and pi a representation in tau x, I will define what's called the principal symbol, what we call the principal symbol, which takes d, x and pi, and will give me a map from C infinity of pi to C infinity of pi. So let's define this. So it's defined as follows. So the first step, you notice that this theorem only applies for homogeneous differential operators. Okay? There's also furthermore, I can add lower order terms, but I have to check the condition on the highest order term. And so the first step is that, let's forget this for the moment, I throw away anything which is lower order. So I make my polynomial homogeneous. So this is the highest homogeneous order part. Okay? Principal part. I also have another problem. My coefficients could be C infinity functions. Just replace the functions with their value at the point. So now when I do this, my polynomial have coefficients which are complex, and it is homogeneous. And then all I do is I can take this and just so this is a linear map because all of these things are linear maps acting on C infinity vectors. So endomorphisms of a vector space, that's an algebra, and so I can take a polynomial in these things. And I get a linear map from C infinity vectors to C infinity vectors. Now we arrive at our theorem. If for all x in M and for all phi in tau x except the trivial representation, 0 is always in the set that I described before. So I always have to remove the representation if this thing, this is injective, then D is hypoelliptic. Okay. So this is joint, as I said, joint work with Andrulatakis and Yunkin. Now, two things. The first thing is that you could ask, okay, does this apply to any differential operator? Because my differential operator I wrote it as in a very specific form, as a polynomial in the vector fields. Okay? And so the first thing is that this is actually not a restrictive condition. So the first thing is that remark any differential operator can be written as a polynomial in the vector fields, where P is a non-commutative polynomial with coefficients in C infinity of n. The justification for this remark is extremely simple. Any differential operator, any Harmander's condition tells you that any vector field, you can write it this way. Because a commutator is by definition a polynomial in the vector fields. If I take by definition, when you take two commutators, this is just xy minus yx. So by definition, a commutator is a polynomial in the vector fields. Iterated commutators are also polynomials in the vector fields. And so Harmander's condition tells you that any vector field, you can write it this way, if you allow coefficients in C infinity of m, because Harmander's condition tells you that they give you bases, and then you linearly span them. So Harmander's condition tells you that you can always write vector fields this way, but any differential operator is a polynomial in the vector fields. And so you are done. And so this theorem, even though I wrote my differential operator this way, in principle, of course, there's a condition which you have to check, because not all differential operators are hypoelliptic, but in principle, you can apply it to any differential, you can check it for any differential operator. So this is the first remark. The second remark, this thing. So when I define this, I used the polynomial in the vector fields. I had to take P of max x pi, so I implicitly wrote my differential operator as a polynomial in the vector fields. I can always do this by this remark. So the second remark, actually it's a theorem. This one's much harder to prove. Doesn't depend on P, in the sense that if my differential operator, I wrote it as a polynomial of the vector fields, and I wrote it as another polynomial in the vector fields, for two different polynomials, then this computation, this is not at all obvious. If pi is in this set. So this is a very crucial point. This only works if pi is in the set tau of x. It's false if not. Okay. Then okay. And I wrote it as a remark, but in reality, proving this is as difficult as proving this. Actually, if you know how to prove this, this is quite easy once. So it's a remark that actually takes time. I want to end with a third remark. This theorem is not if and only if. Not at all. This one was if and only if. This one was if and only if. But this one, no. Okay? The reason is that it's extremely unlikely that we can classify hypoelliptic differential operators. Not soon, not with the current methods, not anytime soon. There are examples of very badly behaved differential operators, which are hypoelliptic, but which satisfy very surprising results. This is a discussion for another course. But we can make this statement if and only if we improve what we mean by hypoelliptic, which will improve the theorem. What Helfer and Norge conjectured was actually a stronger version of this. Okay? So let's improve this theorem. So by this remark, any differential operator, I can write it as a polynomial in the vector fields. And so I can remember that here, when I talked about the order, I didn't mean the order of the differential operator in the usual sense. I meant the order with respect to the homogeneous action. Here on the manifold, of course, I don't have any homogeneous actions. I don't have any dilations and so on. But I can define a new order, or an inhomogeneous order, which mimics this order by saying that it is the degree of this polynomial. So we say that the Hormander's order of P of my differential is the minimum degree of P such that my differential operator can be written this way. Okay? So for example, with the vector fields, I said in the beginning, dx and x dy satisfy Hormander's condition. So if I take dy, this is a differential operator. Usually you would say it's of order 1. But if I want to write it as a polynomial in the vector fields, I can do better than, right? It's not linearly spanned by the two vector fields, but I can write it as a commutator. So it's of Hormander's order 2. Okay? And now I have to erase this. So now we define Sobolev spaces. So we define Sobolev spaces on the manifold. The Sobolev spaces that I will define are not the usual Sobolev spaces. They depend on the vector fields. There are two reasons why I define them. One reason is that it improves the theorem that I just wrote, makes it stronger. The other reason is that I actually need them in the proof. In the last lecture, when I said how to prove this theorem, I had in the end a proposition which involved Sobolev spaces. And actually, I need the Sobolev spaces to prove this theorem. So so these things. So if K is in M, so this thing is the set of distributions in L2 of M locally. It's not a Hilbert space because my manifold is not compact, and I only care about regularity locally. Hypoellipticity is a local condition, such that du is in L2 locally of M for any differential operator d of Hormander order less than or equal to k. If you have seen the definition of the classical Sobolev spaces, it's the exact same thing, but you just replace Hormander order with the classical order. It's the exact same thing, but just so I changed orders and changed it Sobolev space. And now I can state our theorem almost in its full generality. So the following, so M is a smooth manifold. I have to start there, otherwise I'm not. So theorem. M smooth manifold and x1 and xk vector fields satisfying Hormander condition and D differential operator of Hormander order K. Then the following are equivalent. So 1 is equivalent to 2. 1 is equivalent to 2. It's also equivalent to 3. So 1 is the same conditions that we have for every x in M, for every pi in tau x, except the trivial representation. This thing is injective. Yeah, by the way, it's also equivalent to 4. Here I wrote injectivity on smooth vectors. I could also force injectivity on C minus infinity. That would also, that changes nothing. The second is that, so the stronger condition, which is that for every U, a distribution on M, C minus infinity, if and S in R in so this gives you hypoellipticity because, so notice this is Sobolev lemma. Okay? And so if du is smooth, then it's in the intersection of all of them. And so you get that U is in the intersection of all of them, and so U is also smooth. So this is a stronger condition. The easiest way to understand this condition is look at dx on R. So I said in the very first lecture, dx is hypoelliptic, and this is just a fundamental theorem of calculus. The integral of a smooth function is smooth. But you can say much better. You can say that the integral of a Cn function is Cn plus 1, which applies to not necessarily C infinity functions. And so this condition is similar in the sense that it tells you that if you start with du, going from du to u, that's an integration process. You are inverting your differential operator. So it tells you that if you start from du, and it belongs to this Sobolev space, and you invert it, so you integrate it, then it integrates exactly the opposite of the order of your differential operator. So, and this is the best you can achieve. You cannot do better than this one. Okay? Because, again, if you have dx, the integral of a Cn function is Cn plus 1, but you can never prove that it's Cn plus 2. So you have this. And the third is that if M is compact, D from Hs plus K to Hs is Fredholm. Yeah, it's left invertible. Modulo compact operators. I think I'll stop here. I already almost passed my time. Next lecture, I will talk about index theory. And I will also give a computation using this. Sorry, I didn't have time to do computations of tau x or this theorem, but I will try to do a computation in the last talk of a differential operator like this. And we'll actually count solutions of the differential operator using this theorem. Anyway, I'll stop here.